The world's largest aircraft storage facility, AMARG in Tucson, Arizona, holds over 4,000 aircraft, representing billions in recoverable assets. These boneyards are not just graveyards, they are critical supply chain hubs for the global maintenance, repair, and overhaul market, known as MRO. When an aircraft reaches its economic end of life, typically after 25 to 30 years of service or exceeding specific flight cycles, it enters the decommissioning phase. This process is driven by escalating maintenance costs, not necessarily structural failure. The decision to retire an airframe is a complex financial calculation, balancing residual value against required heavy checks, such as D-checks. The primary goal of the boneyard operator is maximizing the return on investment through strategic asset stripping and preservation. Location selection for aircraft storage is dictated by atmospheric conditions to minimize corrosion. The ideal environment features low humidity, minimal precipitation, and alkaline soil composition. The high desert climate of the southwestern United States, particularly areas like Victorville, California, and Marana, Arizona, provides these conditions naturally. Low moisture content prevents galvanic corrosion and microbial growth within complex wiring harnesses and avionics bays. Furthermore, the hard, stable ground eliminates the need for expensive paved storage areas, reducing operational overhead. Aircraft are typically stored on their landing gear, requiring regular tire rotation and pressure checks, even in long-term preservation. The technical decommissioning process begins with fluid purging. All hydraulic fluids, fuel residues, and engine oils must be drained and managed as hazardous waste according to environmental regulations. Engines, which often retain significant residual value, are typically removed first. Airframes designated for parts harvesting undergo a meticulous inventory process, cataloging every component with its unique serial number and maintenance history tag, known as the Authorized Release Certificate or Form 1. Components are categorized based on their flight hours and cycles remaining. For long-term storage, airframes are sealed using specialized protective coatings, often a white, heat-reflective vinyl paint, and all openings, including pitot tubes and engine intakes, are covered with moisture-proof barriers. The core business of the boneyard is the provision of used serviceable material, or USM, which significantly undercuts the cost of new original equipment manufacturer parts. A harvested component, such as a flap actuator or an auxiliary power unit, can be sold for 30 to 70% less than its new counterpart, provided it comes with complete traceability documentation. This market is highly regulated. Every part must be certified by a licensed maintenance, repair, and overhaul facility before reinstallation. The demand for USM is inversely correlated with new aircraft production cycles and directly correlated with fuel price volatility as airlines seek cost efficiencies during economic downturns. Inventory management systems track millions of individual components, optimizing removal based on real-time global demand signals.
Aircraft leasing companies, not airlines, own the majority of commercial airframes entering storage. When a lease expires, the aircraft is returned to the lessor, often requiring extensive maintenance to meet the return conditions stipulated in the lease agreement. Boneyards frequently act as third-party asset managers, performing the required checks and managing the transition. If the airframe cannot be immediately released, it is placed into deep storage. The lessor's financial strategy involves calculating the break-even point between the cost of preservation and the potential future sale or dismantling value. This financial calculus determines whether the airframe is preserved for future reactivation or immediately designated for teardown. Regulatory compliance is paramount, governed by agencies like the Federal Aviation Administration and the European Union Aviation Safety Agency. The airframe's entire life history, documented in logbooks, must be intact to prove airworthiness of any harvested part. Missing or incomplete documentation renders a component worthless for reuse in certified aircraft. Furthermore, the disposal of military aircraft, particularly those containing sensitive technology or classified systems, involves strict export control regulations and demilitarization protocols. These protocols often mandate the physical destruction of specific components, such as radar systems or specialized avionics, before the remaining airframe can be sold for scrap or parts. Modern preservation techniques extend the viable storage life of airframes significantly. Beyond external sealing, internal systems require specialized treatment. Fuel tanks are often filled with inert nitrogen gas to prevent oxidation and microbial contamination. Engine preservation involves fogging the internal combustion chambers with corrosion-inhibiting oil and rotating the turbine blades periodically to prevent bearing flat spots. Avionics bays are dehumidified using dessicant packs or continuous low-flow air conditioning units. The goal is maintaining a stable microclimate within the fuselage, preventing degradation of sensitive materials like composites, wiring insulation, and rubber seals, which are susceptible to UV radiation and temperature cycling. Airframes designated for final destruction yield significant quantities of recyclable materials, primarily high-grade aluminum alloys, titanium, and specialized steels. However, the separation process is labor-intensive due to the complex bonding of dissimilar materials. The scrap value is often offset by the cost of managing hazardous materials, including cadmium plating, mercury switches, and composite structures containing carbon fiber reinforced polymers. These composites require specialized handling during shredding to prevent airborne particulate contamination. The economic viability of final recycling depends heavily on fluctuating global commodity prices for aerospace-grade metals, which are distinct from standard industrial scrap. The aerospace industry is increasingly focused on sustainable decommissioning practices, aiming for 90% material recovery rates. Innovations include automated robotic dismantling systems to improve efficiency and reduce human exposure to hazardous materials. Furthermore, the development of new, easily separable composite materials is crucial for future airframe design, simplifying end-of-life processing. The rise of electric vertical takeoff and landing vehicles introduces new challenges related to battery disposal and recycling protocols for high-density lithium-ion power sources. Boneyards are evolving into sophisticated material recovery facilities, driven by both environmental regulation and the increasing scarcity of specialized aerospace alloys.